Hello and welcome. I'm really hoping that things are okay because there's definitely something wrong with the European internet today. I'm not quite sure what exactly is wrong, but I wasn't able to start the stream to several servers, and this was like the third server that finally allowed me to actually stream to it. So I'm hoping that I will just not disappear in the middle of the stream for whatever reason. And also I had to kind of change my background music today because that software also wouldn't like connect. So very interesting stuff happening today. Let's just say that. So let's start then. And I'm also not like seeing my streaming stats and things, so I hope the chat is actually working. Anyway, the goal for today is kind of well, could be, and welcome to the stream. I'm not quite sure what is happening exactly because like now things seems to be working fine, but yeah, but definitely there was definitely something weird going on, and it's like multiple pieces of software that were affected. So could be something on the backbone, could be something my provider is like losing peering with something. We'll see. But right now everything seems to be stable, so let's just go with it. Okay. Right. So the goal for today, what I really want to get working, at least in some sort of form, is basic support for killer Sudoku in the solver. So yesterday I managed to get the table of sums working. So this is basically a compile time data structure that just lists the possible combinations of numbers that sum up to a specific sum. And it's definitely kind of stretching what Const Expert can do. Right now it even only works for 9x9 Sudoku. If you try to do this for 16x16, basically the compiler will just complain that this is too much compile time, computation for the compiler to deal with. So that's definitely something I will need to revisit at some point. And I mean, right now it seems that the like code completion machinery is actually running the compiler with like stricter limits, and it's actually failing to basically evaluate the const expert things. So right now, evaluation hit maximum step limit, possibly infinite loop. It's not an infinite loop. It's just that it's a lot of computation. Yeah, so today the goal is kind of plug this together and get some basic killer Sudoku working. And we will see how far we get. The big thing that I want to get working first is actually the serialization and deserialization. So for that, I kind of need to think about how exactly do I actually want to store the killer blocks. So let's just grab the notepad for a bit. So let's think about it. So there are two types of killer blocks. One of them is a killer block that has unique numbers, and the other one is just like these numbers need to sum up to this sum, and that's it. Right now the machinery that I have actually only supports the unique blocks, but I definitely want to introduce at some point also which is called like small killer blocks, which is just a bunch of squares summing up to a particular number. So there are two things that definitely define the block, and that will be true for no matter what. So it's the number of squares and the sum. So these two pieces of information I will have no matter what. Now, I somehow need to define the list of the squares. And I think the cleanest way to do that would be just to use the offsets. So basically, you know, if I have a Sudoku puzzle, so this would be offset 0, 1, 2, 3, and if it's just like 4x4s, then you know this would be 4, 5, 6, and so on. So I think that's kind of the cleanest way to refer to each of the squares in the puzzle. And to kind of define the block, we just need to list these. And we know how many we expect because we have the number of squares. So in the current serialization, so let's just actually quickly jump to that. Okay, you know, if I play with something, so the format here is basically just has some basic information about the puzzle. So the first one is like the type of the puzzle, then the dimensions, the maximum limit of the numbers, and so on. And then it's basically just the values. And the point here is that at the very end we can just add like extra information. So let's just say that we start with the type, which in this case, let's just reserve 0 for killer blocks. So this would be like 0 colon, then the number of squares, so let's say 3 for example, and let's say the sum is 9. And then it would just be the offset, so let's say if this would be like 3, 5, well, it needs to be somehow consecutive, right? So 3, 4, and then 13. That would be kind of a feasible offset in the puzzle. So basically what it would mean in the puzzle, it's like 0, 1, 2, 3. So this would be 1, then this, and then plus 9 goes down here. That's the 13. So it would be this kind of block summing up to 9. Now, the question is how exactly do I integrate this into the serialized format? I could kind of have just like, you know, trailing information, and I just like greedily read as long as I have something to read. So then what that basically boils down to, like, you know, serialization wise would be just, okay, like I have one block and then right after that I could have another block just like this, you know, they can just be chained very easily one after each other. And basically when I'm deserializing, you know, as long as I have data, I just keep reading, and always the first value tells me, oh, this is actually killer block. And if I have like different blocks in the future, then it tells me, okay, like this is this specific thing. Okay, what was the limit on the number of characters in the URL again? Okay, so that's like 2002 kilobytes, right? So each of these so if you would have, okay, so the let's think about this. So the maximum offset we can have in a puzzle would be 81, right? Or actually just 80. So 9 times 9, right? But count it from 0, so the maximum would be 80. So this is 2 characters, 2 bytes. So like the upper approximation would be, let's say we just have like the minimum, so the maximum amount of blocks we can have is just, we would have bunch of blocks covering 2 squares. Because single cell killer blocks make no sense, because then, I mean, the sum of one number is just a number, so that's not particularly useful. So at most we could have 40 blocks. Each block would be, so the header is the 0 colon, that's the header. Then the number of squares would be 2, so it's another character. And then just 2 squares, each of them, you know, taking up 2 characters plus the 1 like separator. And then 1 extra column for like the separator. So this would be 2, 4, 6, 8, 10 characters per block. So if we have a killer Sudoku that's like covering the entire puzzle with blocks of size 2, then we are ending up with 500 characters, 500 bytes, which, I mean, that isn't horrible. It is actually quite a lot, but it's not too bad. So for now, I think this is okay. I'm starting to I'm getting the feeling that I will at some point need to kind of revisit this and think about essentially like a binary format to represent this in a much more compact way, and then just like encode it into the URL. Right. But for now, I think this is good enough. So let's actually go and have a look at how exactly we handle the serialization, deserialization, because I actually don't remember. So here we have the serialize. Right, so serialize is pretty straightforward. Okay, so we start with a version, then we just get the grid with the values. Oh, then we have the puzzle type. Okay. Well, right now the puzzle type is just basic and diagonal. Okay, sure, that's fine. And let's say that after the puzzle type we just have like the extra information, which in this case would be the killer blocks. So how do we actually deserialize it? Alright, so we try to read the version and the delimiter, then the row, so then we just read this, and then we just loop and read each square, and then down here we read the type. Okay, and then basically somewhere down here we would have to read the killer blocks. Now the interesting part is actually this. So this method actually sets up the like normal Sudoku blocks, as in the rows, the columns, and the 3x3 squares. Okay. So I'm kind of trying to think where would I actually put the functionality that takes the offsets and transfers that into the actual like killer block, which is a thing I already have a class for, so it's this one. And this actually gets constructed by pointers to the squares, like a vector of pointers to the squares in the puzzle. So I think this needs to be something that lives in the Sudoku puzzle then. Which is actually okay because the deserialize already is in the Sudoku puzzle. Okay. So now, do I want to first set up the checkers and then read the serialized format? Yeah, probably, because so there would be a reason not to do that, but I'm already kind of breaking that. So what I could do is I kind of could try to deserialize, and if that fails, not to modify the puzzle. But like looking at the current code, like that's already happening. Like I'm modifying the data of the puzzle anyway over here, straight up. So I might as well just continue with this destructive approach and just put it in here. So basically when the deserialize fails, like the puzzle is essentially corrupted, like it just needs to be thrown away. Which I mean, it's okay, like it's not a problem. Like it's just one way to do it. Okay, yeah, sure. So let's then put it here after the setup checkers. So this will be like read additional blocks. So first we read the okay. So we read the block type. But let me just check one. Yeah, okay. So after the puzzle type, we still have the colon, the delimiter. So actually over here, we definitely want to do this. And yeah, I actually want to check unexpected Sudoku type information. Right. Oh, I actually do it over here. Okay, sure, that's fine. Okay, but the ordering of this is weird. Like first I should check if I managed to deserialize it, and then I should check the actual value I read. Otherwise it's kind of upside down. Like why? Yeah. Okay. Okay, I think the music is a little bit too loud. Let's just put it a little bit down. Okay. So okay, so let's just do the block, and I'm kind of getting the idea that I should kind of split this up a little bit, because this will become very awkward very fast. Like this method is already pretty big, and especially since basically based on the block type, we can have a bunch of different methods to actually read the like concrete block type. But before that, let's just do block type and delim. So this should right. I need to remember that this is optional information. So actually what I want is while this succeeds, yes, something like this. So while this succeeds, if block type is 0. Hey, welcome to the stream. While the block type is 0, we want to actually deserialize the killer block, which, going back to here, is the number of squares, the sum, and then just the list of the offsets. Cool. This is C++, so similar but different. Number of okay. Killer block. Number of squares, the sum, and then a list of offsets. You used to know how to make websites, as in you forgot, or new technologies arrived? I'm sure you would remember if you would, you know, try again. Like, I have a horrible memory, but it's always like when I start doing things I did at some point, like some of the information comes back. Not everything, obviously. You forget things, but yeah. Oh, come on, 2 years is like nothing. Number of squares. Right. So let's just try to read these two pieces of information. Okay. And while the killer blocks are optional, the moment we basically detected that, okay, like this should be information about the killer block, we can definitely throw errors if you run into something that's inconsistent. So we should have this if over here. Yeah, something like this. Okay, what else? Well, after this, basically all we want to read is the actual squares. So just loop over the squares and just try to read each of them. So this will be a vector and okay, I can do the same idea over here. I just made this error slightly unique. So in general, like, right, if you are throwing different, like, similar errors, it's still worthwhile to kind of have slightly different text messages, because otherwise if you get, you know, one of these triggers, it can be pretty tricky to figure out which one was actually the problem. Right, so once we have actually read the offset, then what we want to do is just put it into the offsets. So push back offset. Right. Now, after this is done, what we actually want to do is add this block to the puzzle, which is actually a thing that I don't have implemented yet. Right. And as I said, I'm kind of tempted to just make this a method. I think that kind of makes sense. So let's just add a very simple method over here. Deserialize kernel block. It will take the same thing as deserialize, or take it deserialize. Here, right. Oh, this takes a string. So no, so this will not be taking a string. What this will be taking is actually an input stream, right? So I stream. Right, and actually let's just put it into the CPP file right over here. Okay, and then over, so this entire inside of this if just needs to move into here, and here we just do deserialize kernel block on top of the stream. Okay, right, I don't have delimiter, so I just need to reintroduce that. But otherwise I should have everything else around here. Yep. And the last thing again that I'm missing is the actual like creation of the killer block. I'm wondering if it makes sense to just put it in here now that I have this deserialize killer block method. Kind of depends on if it would be useful to have a method that just takes the offsets and creates a killer block out of those. Just like as a helper thing to use. It could be useful. I don't know like how much. Probably not too much. Yeah, I mean, okay, let's just put it here. Like, it's not a big deal. So, what we need again is just the pointers to the squares. So, we need to loop. Well, actually, if I'm doing that, I can make everything much easier myself. So, I can straight up just have the squares over here. And instead of pushing the offsets, what I can do is just do data offset, get a pointer of that, so and put it into squares. So this is straight up filling up the pointers to the squares based on the offset. And that's kind of it. Like, then all I need to do is actually need some sort of storage for the kill blocks. So let's just add that over here. Kill block Okay, and I will need to actually include this somewhere. Okay. Include killer block.h. No? Should be working. Okay, well, I'm not quite sure if that actually is working right now. No, we'll see soon. Right, so I have the kilo blocks over here. Do I mind if these get reallocated? Probably that's okay. So if I just do killers and place actually and place back, so it will get the squares, which is the pointers, and I can just straight up move it because I don't need it over here anymore. And then what was the constructor again? It was the maximum and then the sum, right? So the maximum comes from the puzzle, so that was just max, I think. I should have this method, right? No, I don't have max. Yeah, I don't have max. What the heck? Yeah, I should definitely have a method called max. Oh, and I'm just realizing I will need to... It's one thing I didn't do. So for now this can just return size because that's okay. But one thing I didn't do, I didn't actually go and clean up the this interface. There's a lot of like no accept and no discard and those kind of things missing all over the place here. It's not a crazy big deal, but yeah, it's definitely a thing. Right, so then over here I can call the max and the sum I have over here, right? Okay, let's just see if that actually works. Okay, it seems like it worked. Okay, I will need to write some tests, of course, but at least for now it compiles, which is good. So now the serialization. Okay, so now we need to do the opposite, right? So actually I should also have serialized killer block, because again that will come useful. So over here, let's just take another method, serialize killer block, and this will be taking an output stream, obviously, because that's what we are doing when we are serializing. We're writing into an output stream, and this will be reasonably simple. So loop over the kilo blocks and just serialize each of them. Oops. Right. Okay. Obviously, this needs to actually have a parameter which is which block are we serializing. So killer block. Okay. Right. So killer and into the stream, right? And I think check stream, like here I'm not checking the stream anywhere, which I mean, okay, so this is a string stream, and string stream shouldn't really fail unless we run out of memory, in which case we probably don't care that much. What are you complaining about? What? Why would you make it const? Because this is, yes, this should definitely be const. Okay. Yeah, because we are calling it out of a const function, and like serializing things shouldn't modify the puzzle, obviously. It's just taking stuff and writing it out. Binding reference, right, so that's another problem. So this should obviously be taking a const reference to the kill block. Yes, indeed. Come on, refresh. Yes, okay, now it's happy, which is good. So now we can take this and put it over here. Right. So serializing, we do the exact opposite we do into deserialization, right? So let's just take this. So we have to not forget to actually write out the type of the block, because that's one thing we kind of like are doing in a different place in the deserialize. So the deserialize actually reads the type of the block over here and then calls, based on the actual read value, calls the correct deserialize method. But in the serialization, we kind of need to deal with that ourselves. So this will just be write out 0 and a delimiter. Yeah, so this is basically the type of block for killer, which is 0. And then do we have all the methods we need? Size. We have size. Okay, that's good. So we print out the size and a delimiter and the sum, which is k.sum. Yes, we do have that. Perfect. Then another delimiter, and then it's just followed by the offsets. Okay, cool. So then for square in k.get squares, what you want to do is figure out the offset. So the offset would be square minus data 0. So this is the distance of the pointer, because remember that all the squares are in a single dimensional array, so we can do this pointer arithmetic to figure out which square, like which offset we are talking about. So this is this formula, and I keep misspelling unsigned over and over and over every time. And then we just print it out. So what is this complaining? Right, that's fine. Static cast unsigned, because we know we can afford to do this, because we know that the range of the numbers will be reasonably small, because the biggest puzzle we support is 64 by 64 anyway, so that's still quite small, and it will definitely fit into an unsigned. But obviously, like if you just take like any pointer in memory, then you are talking about 64-bit integers, which is not necessarily unsigned. Unsigned usually is 32 bits. But yeah, that's all platform and compiler dependent, but we fortunately don't have to care about those kind of details. So just print out the offset and print out the delimiter, and that's it. So this should be good enough. And basically how this will look like is we go over all the special blocks and try to serialize all of them, if we have more of them, right? But right now we will just have the killer blocks. So okay, let's write some tests then. So we want to see if the serialization deserialization is working correctly. I'm sure I already have some serialize deserialize, yeah, serialize deserialize test over here. So let's just put this test over here as well, and we'll just call it serialize deserialize killer. Oh, and the formatting is damn it. I really need to find the time to like fine-tune these small things that keep irritating me over and over, because it's really grinding on my nerves. Okay. Sure, let's start with like a normal puzzle. And I think what we should do is just manually handcraft a couple of kilo blocks over here. So let's do that. Let's well, it's actually not easy because that's all private data inside of Sudoku. So I would have to create like a helper function that would be a friend of the Sudoku class. And yeah, this kind of in the vein of the deserialized curl block. Sure, no worries. In the vein of the deserialized curl block, but instead of the stream, just take like the number of squares, the sum, the maximum, and just like the list of offsets, and that would just like transform it into a kilo block. Yeah, okay, well, let's do that. So that will be down here-ish. So a friend test inject killer block, and again the things that we will use is the number of squares. Well, actually I don't need the number of squares because I will be passing the offsets anyway in. So I need the sum. I don't actually need the max because the max needs to be consistent with the puzzle anyway. So it's just sum and then std vector unsigned offsets, right? That should be. This should be a good function to do that. Then we can put this function into the test. Right over here. Welcome back, you didn't miss much. Right, but it also needs to take a puzzle. You just noticed that? I thought like my titles and everything are like super Sudoku heavy, so let me know what I can improve to make it more obvious. Oh yeah, I'm missing the return type. Oh, I'm missing the return type here as well. What did I just do? Okay. Okay. So this needs to take Sudoku puzzle, right? Okay, cool. So let's go to here. So now this thing, it will do s.killers.mplace. But before that, I actually need to prepare the vector. So I will need the vector std vector bit set pointer squares, and I just need to loop over the offsets. Break case tutorial? I'm not familiar with that. So just FYI, like 3D games are way harder to like make well than 2D games. And as usual, I feel obligated to tell people, if you want to make a game, realize that the coding is like a tiny part of making a game. A very tiny part of making a game. Unless you are doing like something very specific, like generative, you know, generative levels and stuff like that, where at that point, yes, like maybe the coding will be more heavy, but most of making a game is just like the game design and graphic design and those kind of things. Okay, let me Google this guy. I cannot find this guy. What the heck? Ah, no. Yeah, no. It's just finding an editor instead of people. Okay, back to this. So squares, pushback, pointer to data at the offset, and then over here, so the constructor for the killer block, again I need to remind myself, was the elements, the maximum, and the sum, right? So let's do that over here, right? Oh, this should be s.data. So the squares, the maximum, which is just s.max, and the sum, which I just get as a parameter, right? Okay, yeah, cool. Everything seems to be fine. So now in the deserialize, okay, in not this one, but in this one, what I can do, I can take this puzzle and just inject a killer block into it, right? So I can do, this takes a puzzle, then the sum. So let's do, the sum will be 15, and then let's say that this is, let's say offset 1 to 11. So this will be 1 killer block. Let's inject another one. So let's say this one will be sum 9. It will be just 2 squares. So let's make it over 6, 7. It's kind of good enough for now. What I actually want to see is that when I serialize it, what I expect to see is I should have 0 to denote that this is a killer block, then 3 for the number of squares, 15 for the sum, and then the offset should straight up be the offset I wrote here, so 1, 2, and 11. 1, 2, and 11. And then another killer block, which is only 2 squares, sums to 9, and this one should be the 6, 7. Okay. So then we can keep doing the same stuff. So we try to deserialize it. That should succeed perfectly fine. Then here we just test it deserialized correctly. Yeah, over here I should also test that the killer blocks actually deserialized the same. Okay, let's just put it as a to-do. Well, not exactly over here, because this is just a loop over all the squares. Check that the killer blocks match, right? I mean, sure, you know, one important thing about learning things is just like find something that you are enthusiastic about. So if you want to go for this, like, go for it, totally, like, you know, just be aware. Yeah, I think all of this kind of just remains the same then. And yeah, they should solve for the same. Yes, this all should be fine. So now if I run this test, which is where is it? Sudoku tests, yes, this thing. Okay, so let's see if that works, if it succeeds. And it did. Cool. Okay, so that's great. Let me just double check if I'm running the correct test, because that's always the I mean, I can test it very simply. So if I just change this to a 5, right? Now it shouldn't match anymore. It should actually fail. And it does. Okay, perfect. So that means I know that these things correctly serialize and deserialize. Okay, so now actually we should plug it together, so we actually have the solver try to solve the puzzles. Right, so now I need to go into the smart solver, and now it gets interesting, because now I really need to think about like how and where do I rank the solving technique that I have right now. So right now the only thing I have for solving the killer Sudokus is a very, very simple pruning technique. So if I just quickly jump to daily killer Sudoku, right? So the thing that I have right now is basically it just goes over the blocks, and if it sees that the all the possibilities together actually limit the possible numbers in the square, right? So here it just limits, I can only have 1, 2, 3, 4 in these 2 squares, because like those are the only possible sum combinations that sum up to 5. It will actually go and remove the 5, 6, 7, 8, 9 out of these 2 squares, and that's literally like the only thing that's in the solver right now. I don't think that will be enough to solve even like very easy puzzles. Like this is difficulty 3, so this is like a very easy puzzle, but I suspect it will not be enough. There are some additional pretty simple things I can introduce very easily, but let's just try with this and see how far it goes. This will be a little bit tedious to actually do, but first of all, let's just try to think. So, like doing this kind of propagation where I look at the block and say, okay, like this can only contain 1, 2, 3, 4, 5 numbers, right? How hard of a technique is that? Like it's a pretty simple technique. But I'm not quite sure like where to rank it against the other things. Like it's probably around like block intersection. Okay, let's just say it's like slightly hard, slightly easier than block intersection, maybe on. Yeah, sure. Let's say it's slightly easier than block intersection. So over here, I basically need to go over my killer blocks and try to limit the numbers in the squares. Killer blocks, right. So that kind of means I should have I mean, I either introduce a method over here for that, or I just loop over the killer blocks. I mean, there's this prune some sets. So this these are actually two different steps. So one of them is actually, this one is actually this, like removing the possible sums that are no longer possible. And actually yeah, this one is actually an easier thing. Yeah, I think I will just create a method over here. I guess two methods, alright? Like prune killer block sums and prune squares from killer blocks. So the first one will remove impossible sums from killer blocks based on the square contents, and this one is remove impossible numbers from squares inside of killer blocks. Right. Something like this. So then in the smart solver, yeah, I mean, these two things kind of go together, right? Like I always kind of want to first basically Sudoku dot prune killer block sums. So first remove the impossible sums and then just do Sudoku dot prune numbers from no, not this one. Prune squares from killer blocks, yes. Yeah, these kind of always go together. Okay, so let's just do that. We again check against the solution. All that makes sense. I should also always check my killer blocks if they have a conflict, because again, like inside of the killer blocks, all the numbers need to be unique. Right. Am I actually doing that for the normal blocks? Solution, checking solution. I thought I am checking the conflict somewhere. Not quite sure where exactly, actually. But okay, so what should I call it? Let's just call it unsigned killer sums. So this is literally just propagation based on the sums of the killer blocks. We need to modify this thing. So killer sums plus equals stats killer sums, and the output as well, of course. Right, I can just put it here, sure, that makes sense. Block sums, stats, killer sums. Okay, so I'm printing it, I'm increasing, I have the sum equals implemented. What else do I need? I think I'm fine. So then this thing I need to increase in my smart solver over here, right? And now I actually need to implement these two things, right? So then if I go to my Sudoku class over here, let's just put it in front of the serialization and visualization, right? Okay, over here, for example, that's fine. So so prune killer block sums. So what this will do, it will go over all the killer blocks. Right, and then for each of them prune some sets. And this one will be slightly more complicated, because what I actually want to do here is killer dot unions Yes, this thing. Bit set union. Wow, let's just call it U. That's fine. Okay. So, but now with the union, I want to go over all the squares that are inside of the scalar block. So, auto square. Oops. For this scalar block, get squares. Right, like this. So then square. This thing. Okay, let's just do it like this. And equals U. Yeah, just intersect with it. So this square can only contain the bits, the numbers that are in the union. And that should be good enough. So now then, if I go to my test again, actually not the Sudoku test, this would be the Smart Solver test, right? So I need to create a new test over here somewhere. Okay, this test won't be easy to write. This will be a pretty tricky thing to do. I guess, okay, so like the first thing I can do actually is very simple. Just like copy one of these puzzles straight up. Well, the problem is like this will take forever to copy it. But I mean, this would be like the easiest way to kind of test it well. Okay, let's just try something like one of the easiest puzzles, like difficulty 1. Sure. Let's just try to replicate this puzzle into my solver. Okay, test case solver killer Sudoku. Okay. So first of all, like we don't have any numbers in the puzzle, so we can just straight up start with an empty puzzle. That's fine. The thing that I actually need to do is inject the sums. So actually, what I want is from this test. Where the heck is it? This one, right? The inject kill block. I think I should really create like a small library with test helpers, but for now let's just not overthink it and let's just copy it over here. And this works only for the reason that this is actually, well, this is not exactly the main, but this basically gets just linked against the main. So I now have multiple definitions of this thing, but since I'm putting it into the actual like leaf of the build tree, it's not a problem. But yeah, I should definitely just like refactor this and create a small library with helper functions over here. So what I kind of want to do is just call the inject multiple times here, so it takes the puzzle, the sum, and the list of offsets. Okay. So I will just put this to the side over here. So you will not really see it, but I mean, it is what it is. So the first block is sum 19 and the offsets are 0, 1, 2. Then block of sum 20, 3, 4, 5. Sum 11. This one is 6, 7, and then 1 down, so that would be 16. Then another sum 7, so this is 8, and then 17. Okay. Okay, I mean, this is not too bad. I was kind of worried that this will take forever, but this is actually reasonably okay. So this is 9, 10, 18, and 19. Then, and the good thing is I can then just run deserialize on this, print it out, and then use it in my UI once I have the support for that. So this is 11, 12. This is sum 10. This is 13 and 22. Sum 14. Shockingly, actually, also offset 14. 15, and then the first offset has one thing under, so that's 23. That's for this row. Then the next row is sum 6, and we have offsets. Okay, now I need to think about it. So this is 20. So this would be 0, 9, 18, 19, 20. Yes, that's lining up fine. So 20, 21, and 30. Then the next block is 13. Okay, so this was 20, 21, 22, 23, 24. And 33. So then I have a 15 sum that is 25 and 26. Okay. Then I have a big 17 block that goes 27, 28. And then 2 squares under the 27, so that will be 36 and 45. Okay. Then 11. So this will be 29 and 38. Okay. Another 11. So, okay. 27, 28, 29, 30, 31, and 32. Oops. Then there's a 10 block, which is... Okay, so this was 31, 32, 33, 34, and then 43. Yes, okay, that's all lining up so far. Good. Space over here. Then a big 14 block. So this one is 35. Then 44. Yeah. 53. and then 52 before that, right? Oof, I'm really hoping I'm not making mistakes, because this would be really hard to double check before I actually have the UI support to visualize this. Okay, so then there's a 15 block. That one is okay, so this I need to just double check everything now. So this is 0, 9, 18, 27, 36. So it'd be 37. Does that make sense? 35. Yeah, that is lining up just fine. So 37 and 46, which, yes, that's lining up fine. Then we have a 14 block. The 14 block goes this is 38, 39, 40 and 41. Okay. Oops. Okay, then 12 block. This one goes 42 and then 51 because it goes down. This I already have, this I already have. Then the next row, okay. We are getting there. This is a 9. This should be 50, 56. Let's just double check if that makes sense. So this is 0, 9, 18, 27, 36. No, wait a second, what the heck? No, yeah, correct. Good. So this is 40, 45, 40, 47. 47. This one, yeah, it's just below this one, so yeah, that makes sense. So 47 and one below that is 56. Cool. Then a 15 goes 48, 49. Okay. 15. Then a 6 goes 50, 59 and 60. Okay. Then let's just double check next to that is the 12. So 51, yes, that makes sense, that lines up. Cool. Then just a couple of the last ones, well, the last 3 rows, but there's not too many blocks in there. So an 11 that goes from 54, 55, and it should be just below the 17, which is this one. Yeah, so that's 45, 54. That works. Then there's an 18 block over here. That is 57. Then one below that is 66. And one before that is 65. Okay. Next to that is a 7, which is 58 and 66. No, 67. Sorry, almost made a mistake. Then there's a 24 over here. So So this is 59, 60, 61, 62, this is 70, 71. There's a 10 over here, that's just below the 11, this one. There's 63 and 70. What? No, not 70. What am I doing? 72. 10 and 11 over here. So this is 64. Just below that is 73, and then 74 next to that. Alright. Oh, I'm so looking forward once I will have this implemented in the UI. Unfortunately, the UI right now is frozen because I am waiting for a new release of the Clang compiler. So this thing is, oh geez, so this is 64, 65, 66, 67, 68. And it should line up what? Yes, 68 below this square. Yes, that makes sense. So 68, 69, and then the last two blocks, there's a 20 that goes geez, so this is 72, 73, 74, 75. Let's just double check. This should be below the 18 over here, below this, no, below this square. So 75, yes, that makes sense. So 76, 77. And the last block is this one, which is an 18, which just continues. So that's 78, 79, oops, 79, 80. Okay, so we have all the kill blocks. So what I now want to do is to actually try to solve it. I mean, basically this thing. And I mean, I basically just want to print out the puzzle, so just test dot. Well, okay, first of all, let's check test is set, which actually checks if the puzzle is solved. But before that, and I guess I can keep it info, which will only print out if the check fails. So test.debug string. Yeah, let's just like grab the puzzle, print it out if it's not set. Okay, I really have no idea if this will actually solve the puzzle, because again, like, this is a very simple technique, so I kind of doubt that it will, but it might. And things are not compiling. Oh, because I don't have the stats, right? Okay, once more. Oh wow, is it actually managing to solve the puzzle? That's crazy. Well, okay, let's sure, let's do warn this. Actually, there's another warn. Let's just get rid of this for a bit, so it doesn't poison the output for me. Well, okay, this doesn't look solved. What the heck? Smart server. Oh, I'm doing the opposite thing, damn it. Yeah, okay. But this is weird. So this literally didn't do anything at all. Which... right. Okay, I think I know what's the problem. Because in my smart solver, I kind of assume that at the beginning I have... Yeah, okay. So basically because I don't have anything in the puzzle... This just bails out immediately. Damn it, how do I do this? Like I kind of want to at the very beginning have everything. Yeah, essentially like if I have killer blocks, I kind of want to at the very beginning have everything marked as changed, because well, technically not everything, just the squares that are part of the killer blocks. Damn it, how... Okay, so I think what I should actually do is, as the very first step, do this thing. Even before I do the change blocks. I don't like this because this is it's pretty annoying, but I guess it's a reasonable quick fix. So basically what this will do, it will go over all the killer blocks and it will basically like eliminate the possibilities that cannot be in those squares based on the possible sums. So then immediately the change blocks will work. Or actually, let's do it differently. Let's do this actually in the test, because I really don't like having this in the actual puzzle. So let's just call it on the puzzle. This means that the puzzle will actually start with modified blocks and we should see something happening. Okay. Yeah, so it's not able to solve it. Well, let's just look at if this output actually makes sense. Okay. So let me just drag the puzzle to over here. Okay, it's a bit kind of hard to fit everything onto the screen. Ah, damn it. Yeah, the problem is I also want to see this. Okay, I guess we can just scroll a bit. Right, so these three squares cannot have a 1 based on the sums. So, okay, that happened, that was removed, that's good. These cannot have a 1 or a 2, which also happened, cool. Then this 11 block, yeah, there's no 9 in here, which also got correctly removed. this one also lost to 1. Interesting. Then this one cannot have 7, 8, 9, which correct. Okay, so there was definitely some more propagation happening as well, because like there's a 1 that could just disappear from here. Okay, actually what we can do is over here also do warn stats. Oh, I don't have a debug string on the stats though. That's a bit annoying, but oh, okay. Is there okay, just looking around, is there something? No, it looks like this all could correctly propagate. It's just not enough to actually solve the puzzle, unfortunately. Yeah, but this definitely works. I mean, at this on, well, not definitely. On the first glance, this works. So, okay. What's the time actually? Oh, I really need to take a short break. Yeah, so see you in 5 minutes. I will just take a short break, and then once I come back, I will actually look at implementing the some of the other techniques of solving the killer Sudokus. I will stick with some simple stuff for now. But I was really hoping that this would be slightly more successful than it was, but yeah, okay, we'll see. See you in 5 minutes. Okay, and I'm back. So, time to implement some better solving techniques. So let's have a look at this again. So there are actually quite a few techniques that kind of could do. So one of them is basically figuring out remainders. So for example here, the sum of these blocks is 43, which immediately means that this has to be a 2. Why? Well, because this 3x3 block has to have numbers from 1 to 9, which sums up to 45. So if I know that this is 43, then this has to be a 2. And I kind of can do it in a more generic way, right? Like here I know these two add up to 10. And I know that these two need to be different numbers because they are contained within, you know, this block. So I can just introduce another killer block that just covers these two. And if I basically do it for every, you know, every possible block, like for the row, right? Like I have these two that add up to 39, so it means I know that these 3 add up to 6. And again, because this is within a row, these need to be unique, so it can be a proper killer block. So essentially, the tricky part is it's not easy to figure out these intersections. Like it's not easy to figure out basically which squares are like the remainder. Like if I go the good thing is I can actually do this once at the beginning. Like I can figure out these mappings once, right? And that's kind of it. Like I don't have to revisit this like over and over. It's a stable thing that just remains the same across the solve. But it's the problem is it's still a very complicated routine because there really isn't any better way to do it. I don't think. At least I cannot really think about the better way to do it than just go over all the rows, columns, and, you know, 3x3 squares, and for each of them literally figure out which squares in this block belong to like a killer cages that are also fully contained within this block. Oh, which is, yeah, jeez. Okay, that's not. I mean, one thing I can rely on is like if I have a list of squares, it's always in a sorted order, so that helps a bit. Like I don't have to. I can basically make a like if I'm checking the killer cage against the block, it's just a linear search. But it's still a lot because I need to check like every every block against each killer cage, essentially. Which is quite a lot of checking. I'm trying to think if there's like a easy way to do it. I would need some. I could like reintroduce some special data structure that would help me with this, but honestly not quite sure what that would look like. I have an idea. So in my solver, what I already have is like I can take a square and basically I have the reverse mapping from the square to like rows, columns and the blocks. So what I could do is for each killer square go over this like reverse mapping, which is already pre-computed, and if each of the like basically compute the intersection of these mappings, right? Like so. Okay, let's just jump to the notepad. So let's say we look at the 0, 0 square, right? And that one tells me that the blocks that this square participates in is the block number 0, which is like the, you know, first row, block number 9, which is like the first column, and block 18, which is like the first 3 by 3 square. But if I ask row 0, column 1, what I get back is still block 0, block 10, which will be like the second column, right? And still block 18. And if I ask for 0, 2, I get the same idea again. It's still the first row, the column changed, so this is now block 11, so this is the third column. But this remains block 18. So if I look at the intersection of these three things, I end up with block 0 and block 18, which means that this killer cage is fully contained within these two blocks. And I don't have to do like crazy checking. Like this way I can figure it out from the killer blocks, go to the blocks. So then basically what I want to store is, yes, so once I figure this out for every killer block, I just need a map of block ID to killer block ID. Well, multi-map, I guess. Yes. And once I have that, then I can just iterate over this map, and for each block ID figure out the remainder and insert a new killer block. And I guess I guess what I might want to do is kind of I probably don't want to start with just doing this for all the remainders. I mean, that would be a very strong solving technique, but I probably don't want to do that, because because like human players will not go and like, I mean, this is an easy puzzle, so there are not really amazing examples, but let's say here, right? Like, I know that this is 27, which means that the remainder is 18, right? So with the remainder 18, I have 4 squares, so I will probably not like remember that these 4 squares are like a virtual killer block, right? That would be a little bit nuts. So I probably want to, like, at the beginning compute this multi-map, but then basically have like add remainders of, yeah, have like a method that's like add remainders, which is a solving technique, right? And then what we can do, we can, in the solver, we can basically go and say, okay, like, if I'm just doing simple techniques, I just do add remainders 1, right? And if I'm stuck and I need to like ramp up the solving power, I would just then do add remainders 2, and so on, right? And I can basically track this, like this is pretty easy to track. And considering like so I can make the add remainders to only add basically the, you know, the remainders of that specific size. So this way these don't ever add the like anything conflicting, right? So it's like very much clear what's happening here. Oh, I just realized one thing. I'm totally missing. Yes. Okay. There's one thing I am completely missing. So what my solver will do in this case, like if I put a 2 here, it will not even, right. I need to do some work over this also, because I don't think my solver will actually figure out that this needs to be a 7, as it is written right now. Yeah, so this is almost like what I basically want to do here is the moment a square is set, I actually want to kick it out of the block. Right? Am I saying that right? I know, I can actually make it easier, right? So, okay. I'm totally forgetting about a bunch of things that are already supported in the solver. Okay, so the only thing I want to do is, right now I have the kind of look at the squares, union them, and then basically, is that correct? Damn it. let's go to the killer again. Where is it? Right, so return the union of the still possible sets for this killer block. Right, okay, so I have take all the possible sums, union them, and then just intersect it with these squares. So that's one thing. The second thing, the other way around, is right, union the squares, and if basically the union of the squares doesn't end up working for one of these sums, then just remove the sum. But there's also a thing that works from like a single square, because so if I look at a single square, the single square has to intersect with one of the sums for sure. So in this case, what that will do is it should basically eliminate these three out of the possible sums, because I'm saying that this square needs to intersect with one of these. And the same thing, so even if this was 2, 7, like if you figured it out that this has to be 2, 7 from through other means, the 2, 7 only intersects with this possibility. So, you know, something like this should happen. And that, you know, even if I had a 9 here, that doesn't change, you know, this step, because again, like this only intersects with this. Right. So that's definitely a technique I should have. So go over all the squares of a killer block, and each of the squares must have an intersection with one of the sums. Okay. Or to put it other way, like if the square doesn't intersect any of the sums, then just remove the sum. But not whatever. If the square doesn't intersect one particular sum, I just remove the sum. Okay. That actually might be stronger than this prune sum sets, like through the union. It might be like a straight up superset of this rule, because I definitely feel like this is actually a weaker version of what I just said. But for now, let's not delete it. Let's just write a second one. Prune sum sets by square. So let's not do this step, but instead let's have this loop actually inside of this thing. And what I want to check in here, if possible sets so if this is still, like this sum is still possible, I mean if I think that this sum is still possible, and the sum itself, which is just this, intersected with the square, is count set is 0. Right. So if the square has no intersection with the sum, then just remove the sum. Okay. And just to see Yeah, when I'm pruning, let's just do both. And let's see if that actually changes the output here in the solver at all. Because again, I think what I just said is actually much stronger rule. So maybe this will actually improve the situation. Doesn't look like it did. Okay, but this, I mean, this still is correct, right? Okay. So let's do the remainders then. So as I said, at the beginning, I want to basically do the preparation work, which is the building the map. And then during the solving, I want to kind of involve the different generation methods at different strengths even. Right, so let's do this. So where would I do the preparation thing? I mean, that almost... Yeah, like this kind of also belongs in that area, like the prune squares from kiloblocks. It's almost like I should have like a special method on the puzzle that just like builds these data structures and does like does the first step to like prepare the puzzle to be solved. But I guess for now I can just like call it manually. That's not a huge deal. So let's just try to do that over here. So as I said, okay, let's go back to my notes. So it should be a multi-map from the block ID to killer block ID. So these are just indexes in these two vectors, right? I have the checks, which is the blocks, and I have the killers, which is the killer blocks. So I will have an std unordered multi-map of unsigned to unsigned. And this is the contained killer blocks. Right. And I need a method to actually calculate this, right? So for now I will just make it public, but again, like I kind of want to wrap this up afterwards too into like a neater package. So pre-compute the mapping of killer blocks into standard Sudoku blocks, rows, columns, squares. Okay. Pre-build killer mapping. Oops. Right. So what this thing will do, as I said, is I already have the mapping from each square to the blocks the square belongs to. So we will use that. So this will be looping over all the killer blocks. And inside of each killer block it will loop over all the squares. And here yeah, right, so I need to Damn it, how do I do this? I kind of need a set. Is there... Okay, CPP reference, I need you. CPP reference. For set. There's a merge. Erase if swap. I'm trying to figure out if there should be. I think there's an. It's probably not called intersection. Oh, set intersection. It is called intersection. Cool. So. Right. Okay, what is this actually expecting to get? Right. So I could just do this on every step. The block mappings should be sorted, I think. We'll have to verify that, but basically I should be able to do this on every step. And that should actually be enough. Okay. So maybe this will be pretty easy then. Oh, but right. Yeah, okay, so it's probably not that easy, because yeah, no, okay, that will be sorted for sure, because I first insert the rows, then the columns, then the 3x3 squares, then optionally the diagonals. Okay, now cool. So this should be all sorted. Except maybe for the diagonals actually. No, the diagonals will be also sorted. Yes, okay. Oh geez. Right. Where the heck was I? In here. So I cannot just do a range loop over here because I actually want to start with... Okay, let's do it like this. Get squares 0. Okay. So I'm kind of relying on the fact that I always have at least 2 squares inside of the killer block. So what I will do over here is get the first square. Now the position of the, I mean the reverse mapping, block mapping, I need to figure out the offset of this square, which will be data 0. Get a pointer out of that, so first minus this. Static cast to unsigned. Okay. So then this will be offset. So the first dimension is rows, so this is offset divided by size, and this is offset modulo size. And that will be the first value for the intersection. Okay. And then what I want to do is go over the rest of the blocks and keep just updating the intersection. So what's the best way to do that? So for S1, which is less than killer get squares dot size I plus. Let's grab the current mapping, which will be very similar to this. Offset, well, not offset, let's just call it yeah, it's a little bit annoying, but I mean, okay. Basically, this is the same thing over here. And this entire loop is kind of very ugly. I'm not quite sure what to do about that though. Like, it's kind of, I'm doing the same thing outside of the loop as inside, which I really don't like, but kind of need a preparation step over there, so yeah. Okay. So this, just in something like this, it's the current, and then what I want to do is do the intersection. So the new intersection, std set intersection from intersection.begin, intersection.end, current.begin, current.end, and then out. What was it? Back inserter is std back inserter onto new inter, right? And then basically what I want to do is intersection swap with new inter. Okay. So I look at the current square, I get the block mapping of the current square, then compute new intersection based on the previous intersection and the current block mappings, and then just swap the intersection with the new intersection. Once I have done that for all the squares, then what I want to do, if well, actually a for loop over the intersection. So auto block, not this, the intersection. Yeah, not quite happy with how this code looks because it's not particularly readable. But I'm I could maybe write a helper method for just this step, basically. Given a square, get me the block mapping. It's actually not a horrible idea. Okay, let's do that. That will make the code much more readable. So that will be a private method somewhere here. So it will be the std vector, this thing basically. Get block mapping out of a bit set pointer. What the heck? This can be const. So what this will do is basically the logic that I had over here. So these three lines essentially. So like this. So calculate the offset based on the square minus data 0, and then get the return the block mapping. And then over here I can just do intersection is get block mapping from this. Okay, and this can go away, and the same over here. Get block mapping. Okay, perfect. Yeah, that's much better. Okay. So then I go over the intersection. I have the blocks. So what I want to do is actually, I kind of need to know the index of the killer block. So actually this loop needs to be yeah, something like this instead, which makes, well, I can still do auto killer equals killer ID. Yeah, okay. And then over here, then what I can do, so I have the block, I can figure out which block it is. So unsigned offset is block minus what's it called again? It's checks, right? Yes, checks. So figure out which block it is. Yeah, maybe actually for this also I should just have like a get offset method somewhere. Yeah, maybe this would make sense, because I keep doing this a lot actually, like for both the squares and the blocks. But anyway, okay, so I have the offset. So what I said I want to store is the block ID to the killer block ID. So the, what did I call the map? I called it the contained killer blocks, right? So contained killer blocks dot insert make pair of offset and killer ID, right? So after this runs, I should have the contained killer blocks filled in with all these things. And I kind of think I should test this. So let's go in here. Inside of the test where I had the killer blocks already. Or was that in the solver? Might have been in the solver actually. But I did also test the killer over here somewhere. Not this one. Yeah, over here. Right, but I only have like two very simple blocks. Right. No, but this is actually fine. So, right. How do I test this? So let's just draw this. So the 1 to 11 is basically this. Come on. Let's just delete it. Okay. So the 1 to 11 is basically this situation. So this is fully contained within both this square. Well, just this square, right? The offset 6, 7 says 0, 1, 2, 3, 4, 5, 6, 7. So this is, well, like this. So this one is contained within the row and this block. So I can definitely test on top of this data. It's just that I don't actually have the access to the map here. Right. So I guess what I should do is just create another helper test function. This is all a bit annoying. So friend this thing, right? Test get block, not block mapping, get kill contain, damn it, I don't know what to call it. Get contained killer blocks. Let's call it that. Right. And I mean, this thing I can actually write inline because this is very trivial. This will be just return this thing. Where is it? Contained killer blocks, yes. Okay. And this should definitely return a reference. Yep. And we should take the puzzle as a reference and actually return the s dot. Right. Okay. So we have this. Then in here, what I can do somewhere doesn't actually matter that much where exactly I do that, but let's do it before the solve. Sure. So let's just grab the mapping, and as I said, I expect this to be, so let's just do a bunch of checks. So note request, so check mapping.size should be 3 because the first killer block is contained within one thing and the second one is contained within two things, so there should be total 3 unique records in there. And it's not as over here, it's test. Then mapping dot count well, actually, wait, does a unordered multi-map actually have a brackets operator? I don't even know. Multi-map, unordered multi-map. Yeah, no, it doesn't have brackets operator, which kind of makes sense. But I can just use find instead. Right, so find me things contained within the first row. So this should definitely return a thing. Mapping dot end. Find me the first square, which will be 18, and find me the this square, which is, so if this one is 18, 19, 20. Okay, so all of these should return something. Okay, let's just actually, so auto first row, let's just be very explicit about this. So first row mapping and should be fine. First square 18. Okay. And this thing over here, this is auto third square. Right. Okay, so this should all be true, but actually before I do that even, I need to still do test.prebuild killer mapping, right? Because this is actually, I haven't called the method that builds the mapping. So let's switch to the Sudoku test and run it. So this should not be failing. And it doesn't even compile. Okay, what did I screw up? In file, what the heck is happening? What the heck? I mean, find should return iterator. Oh, maybe. Yeah. I think I actually want the equal range thing. Yes. Yeah, it's a fair point. But yeah, I don't think this is actually causing the issue. Oops. Yeah, not quite sure where this is actually coming from. Okay, let's just comment this thing out for a bit. Because it could definitely... No, so this is fine. So it's really these comparisons that are screwing it up somehow. I mean, I can make them simpler, so I can basically check, like, let's forget this. I can just do count 0, should be 1. the same for the 18 and the 20. And I'm hoping that this will not cause any issues. Yeah, so this actually is fine, but okay, then what the heck is exactly the problem here? So if I do mapping equal range for a 0, and if I really do first, so if I dereference first, because I know there's at least one, so just dereference first, second should be I'm starting to get an inkling what was the problem. So this should be a 0, yes. Well, let's just see if this works. Thanks for the follow. Let's see if this now works. Interesting. So this is a 1. Ah yes, because the block contained within the first row, if I go back to the UI, is this one, which is the second one. Okay, so this indeed should be 1. Yes. Okay. And the one contained within the first block should be the 0, and the one contained within the third, I mean, not block, square, should be 1. Okay. So this should all be true now. Let's see. Yes, okay, cool. So this is working. Right, so now I have the pre-built mapping of things. So now I kind of want this method, the add remainders. And actually the add remainders one is special because that actually shouldn't be adding any new blocks. Since, so if the remainder, let's just jump to the, there was like, it's actually this example, right? So if I have this kind of situation, right? Basically I have everything but one square covered by the cages. Then I don't have to create anything, I can straight up set this to 2 and be done with it. Yes. Okay. No, cool. This is very cool. So for the one, this will be slightly special. It will not be creating any killer, any new killer blocks, but the 2, 3, 4, whatnot will be creating new killer blocks. Yeah, there's like example here. Like these two should be 5 together. There's another 1 square here, which is a 9 because this is 36. There's a 2 square over here, which is a 3 together, so this is 1, 2, obviously. This one is the big one, which is like 4 different squares that add up to 18. There's a 2 square one, which is 32, but actually this is a, we know this is a 7. So this was 13 before, so this then ends up being 6, and so on. Yeah, cool. And like this kind of propagation would actually happen naturally, because it's like, okay, I add a killer block that is a 13, but the moment I set the 7 here, this becomes a 6. Yeah, cool. Now this I'm getting a good feeling about this approach. This will work nicely. And it also has like the nice cadence of For easy puzzles, I will just do the singles like these corners, and if that actually solves the puzzle, then everything is perfect. If not, then I will ramp up to like bigger fake killer sums. Right, so this can go away. Right, okay. So where should I have this method though? That's a good question. I should have this. I should have this on the Sudoku puzzle. Right. So, considering that the add remainders 1 is doing a special thing, I'll just call it add killer singles and add killer remainders, and this will take an unsigned size bigger than 1. Right. And I really need to take a short break, but I will be back in 5 minutes, and I'm still kind of hoping that I will actually manage to finish these methods in this stream and then see if it actually can solve the puzzles, at least some of them. That would be very neat. See you in 5 minutes. Okay, and I'm back. So, as I said, the thing that I need to do now is introduce these two methods, the add killer singles and add killer remainders. So let's do that. So go over here. Alright, so for single remainder squares, just set them to a specific number. For multi-square remainders, create a new killer block. Okay, so let's just copy these things over to here. Right. So how do we actually figure out that this is the case, that we have a single remainder? Well, we need to first of all loop over unsigned block ID less than checks dot size block ID plus plus. So we loop over all the blocks, and then we look into the pre-computed map. So dot equal range for this block ID. Right. So we get the range of the killer blocks that are actually contained within this particular block. And then if we actually look at the number of squares, then we can very easily figure out, if the number of squares matches up with the number of squares in this block, right? So then for auto iterator is range dot first, iterator is not equal range dot second, iterator plus plus. So then iterator, right, so here I'm actually interested in the second, so the second, so right, so the equal range returns a pair of iterators, which is like the beginning and the end of the range of items that have this key. Then for each of those, the iterator first is still the block ID, it's the key, but what I'm interested in is the actual value, which is iterator second. Now, this is the index inside of the killer blocks. So killers, this is actually the killer block that I'm looking at. Then what I actually want to do is get square, well, actually I should have size straight up, yes. So what I can straight up do is unsigned num squares, start with 0, just do num squares plus equals this, and then down here, if the num squares is checks block ID dot size -1. So if the killer blocks cover all the squares but one, at that point I need to do actually two things. I need to figure out which Which square is not covered? Okay, so that's actually not easy. Damn it. Like figuring out what value it should have is pretty easy. So that's right. So yeah, here I actually need to figure out which square is not covered. And then what value it should have is sum for the size of the puzzle minus sum of all the killer blocks. So that actually I can do over here. So killer sum plus equals killers iterator second dot sum. Right. So how do I do this? Like when I'm looping over the killer blocks, I kind of need to remember which squares I have seen through the killer blocks. So there will need to be a loop over here, go over all the squares within the killer block. And I'm just realizing that actually this piece of code I guess until here, like this part will actually be shared between the two methods, between the addKiller remainders and the addKiller singles. So I will need to do like a helper method here. But I definitely need to go over all the squares within the killer block and somehow mark off the squares that are in this block. Yeah, okay, let's do it this way. So I start with a vector bool of let's call it found, and at the beginning it will be initialized to block, well, to checks block ID dot size false, right? So this will represent whether we have seen the like corresponding square inside of this block. So then over here, go over all the squares inside of the killer block. So auto square killers second dot get squares. Right. So iterate over all the squares within the killer block. And now I actually need to search the squares of the, yeah, so this will be a double loop. For auto b square checks block id dot get squares. If square is b square, then shoot, okay, that this actually needs to be a normal loop because I need to know the offset. Yes. Checks block id dot size I plus plus. If square is checks block id dot get squares at I, then found at I is true. So if we manage to find the square inside of the block, then just mark it off in the found. And then basically in here we know that the found basically has false at only one position. So actually maybe this will be easier if I just make it I was thinking about making it a set. I could then just like remove the things out of the set as I find them. Yeah, actually, that sounds like a much better idea. So let's just make this std. Well, for this size, it really doesn't matter what I actually make it. Let's just make it unordered. Oh, actually, why am I even complicated? This should just be a bit set. Right. Yes. Of course. Ugh. Obviously. Like I have a high performance data structure for representing sets of things, and I don't use it. What am I doing? Right. So bit set found. This will start with bit set Sudoku square of size. Yep. So what I want to do here, instead of this, I want to do just found minus equals I plus 1 actually. Yes. Okay. So then over here, what I can then do is found dot, well, it definitely should have has singleton value, so I can just do an assert over here. If it doesn't, then something is broken, because I know that num squares, like there's one square that wasn't found, so there should be one bit remaining in this thing. So found dot singleton value should be just the ordinal number of the square in the block. So the actual square is block id dot get squares at found.singleton value -1 is the actual square, and what I actually want to do is set its value. Should be checks, right? Auto square is this. So square set no just override the square so it's a bit set single bit. So the max value is checks block id dot max, and the actual number is the sum for the size minus the sum of the killer blocks. So the killer sum is the sum, but I'm somewhere I had the mapping of the sums for different sizes of the Sudoku puzzles. I remember writing that somewhere. The question is, where the heck was that? Block checker. So this is like the old code that I was doing. Did I have the mapping perhaps here somewhere? No, it doesn't look like it. Well, okay, maybe I did have it, but I removed it at some point. Well, doesn't particularly matter, so let's just reintroduce it then. So but I did have an I definitely had things like this. Damn it, where is that? Oh, here, yes, block sums. This is the thing I'm looking for. So I do have it. Okay, block sums. Where's my function now that I was writing? Here. So block sums for this thing for the size minus the killer sum. Okay. Okay, very complicated, but this should be working. Let's just go through it step by step. Right, so we go over each block, then we remember which squares we have not yet seen. So at the beginning we haven't seen anything, so this is just initializing this thing with like all the bits set. Then we find all the killer blocks that are contained within this block. We loop over them. We remember the number of squares we have seen, the sum, the total sum of all the killer caches we have seen. And again, this is just for the fully contained ones. If there's like a cage crossing between blocks, we don't care about those. We get the squares of the killer block. We figure out which square that is in the block, mark it off in the found thing. And then down here, if we have seen all but one square, the found should have only one bit set, so it should have a singleton value. So then we can just grab the corresponding square out of the block, and then we can just set it to a specific value. And why is this complaining? Not quite sure. No viable. Oh, because this is a wait. What? Why would there be no variable overload? I don't get it. This has type const. Why? This is not a const method. Oh, block sums is const. Sure, let's just do add. I mean, yeah, whatever. Like this will throw if the size is not in the map, but I mean it should always be in the map. Okay, so then we can take this and we can actually call it from the solver. So in the solver, actually I would say this is a very simple thing. So this should be like, well, okay, I have all the killer stuff at the same place, so let's just continue with that idea. So let's just put it over here. Add killer singles. Okay, so oh, unused parameter. Sure, I can live with that for now. Okay. Yeah, so this is working, and now the big question is the solver test. So this is the one that actually has the example of the puzzle. Yeah, okay, so this is not working, I don't think. Let's just jump into the smart solver test. Oh, but I'm actually not doing the test.pre-built kernel mappings, right? Okay, that's why it didn't work. Let's try again. Okay, this looks way better. We have some solved squares even. But it's still kind of meh. Okay, so what's the, so it did figure out this 4-9 and this 2-7. It did not figure out this 6, which makes sense because this kind of needs these two squares. What else did it do and not do? Okay, interesting. So oops. One, two, four, five. Yeah, so this is one limitation I'm not liking because, but I'm not quite sure how to implement this. So this cage here, so since it is a 6 and I know that the 1, 2 has to be here, I clearly cannot have a 1, 2 over here, because that would imply there's a 4 or 5 here, which there isn't, right? But the solver thinks that the 1, 2 is still possible here next to the 4, 5. Right, so this is, I should almost be looking at like subsets of these. Interesting. Like, yeah, okay. This is an important rule, but I'm not 100% sure how to implement it yet. Is there anything obvious that the solver should catch based on just like these simple things? Three, 8, 5, 6. And so I mean the propagation is working correctly. The 11 got eliminated to 3, 5, 6, 8, which is correct. Yeah, okay. So there is still a lot of work to get this working, unfortunately. I mean, okay, so if I do the most of the time, right, okay. If I do the multi-square blocks, I think that will end up in a better situation, but that's like way, like I don't like it because that's not really what people would do. It's not like a human-like solve, honestly. But it definitely makes sense to just have it implemented. So as I said, there's a reason to extract basically this piece of logic out of here. So basically this is like like a helper method over here that will be like a figure out. So for block ID, figure out the num squares, the killer sum, the found. I guess that's it. So what will I call it? Void process contained killer blocks. Right. So this will be taking the block ID as a parameter, and then it will spit out the num squares. The killer sum, the found, and that's it. I think I said right. So this goes over here. Okay, so I will be just calling it from over here. Right, like this actually. Okay. Oh, and I'm misspelling unsigned again, as usual. Alright. So process contained killer blocks for block ID, num squares, killer sum. Come on. And found. So this thing goes over here. The only thing I want to do is reinitialize these. So num squares goes to 0, killer sum goes to 0, and the found gets set to this. Right. So then for this thing, instead of checking the -1, we do minus size over here. And now this piece is a bit more complicated because instead of just setting the square to a specific number, we get a bunch of squares and we want to create a new killer block. So, okay. Right. So this, I will need a vector of bit sets, pointers to bit sets. So this will be the squares. I need to iterate over the bits in the found thing. So bit set bits out of found. And no, no matching. What's the constructor? Oh, it needs a pointer. Sure. So get squares, right. Oops. Insert this thing in there. And once I have that, I can do killers dot and place back the squares, and this should be an std move because I don't need this vector after this point. Then what was the constructor on the killers again? I keep forgetting. What the heck? Right, it's the max and the sum. Right, so the maximum is the same as the maximum of the block, so that's this thing. And the sum is this. Cool. I mean, okay, let's just okay. So one thing is, like, this should really be just run once, because otherwise it just will keep inserting the killer blocks, which is very silly, and it will just make everything slower. So honestly, what I should do is just test.add killer singles over here, test.add killer remainders for size 2, size 3, size 4. Oops. And remove it from the smart solver. Which was over here, right? Yeah, I mean, this is a thing I will need to figure out somehow, because like so far we actually managed to solve it now. Cool. So let's just double check if this is making sense. I will just write it on the side. 6, oops, 8, 5, 4, 9, 7, 3, 2, 3, 4, 9, 6, 2, 1, 8, 7, 5, 2, 7, 1, 3, 8, 5, 4, 9, 6, 5, 6, 8, 1, 4, 9. Okay, I made a mistake somewhere. 5, 6, 8, 1, 4, 9. Oh, I'm reading the wrong. Okay. I was one line off. 8, 3. Oh, what the heck? I completely screwed this up. Okay, let's just reload. Reset. No. How do you reset the puzzle? Start again. Right. Okay. Let's concentrate, and it's the end of the stream. My concentration really is going downhill, but I really just want to verify that this is indeed the correct solve. 3, 4, 9, 6, 2, 1, 8, 7, 5. Then we are at this line, so it's 2, 7, 1, 3, 8, 5, 4, 9, 6. Yes. Then I'm at this line, 7, 1, 3, 2, 5, 6, 9, 8, 4. Yes. Then this line, 5, 6, 8, 1, 4, 9, 7, 2, 3. Then here is 4, 9, 2, 8, 7, 3, 5, 6, 1. And 8, 3, 7, 5, 6, 2, 1, 4, 9. Then 9, 5, 6, 7, 1, 4, 2, 3, 8. Okay. Then 1, 2, 4, 9, 3, 8, 6, 5, 7. Okay. So that was correct. So this can solve some simple puzzles, but there are a few things I'm not happy about. So first of all, again, the creating these sums across multiple squares. Like when I'm solving killer Sudoku, it's a thing I would do from time to time, but like definitely not for like 4 squares. Like that's crazy. And also, okay, let's just, if I do start again, there were these situations where like I managed to like, okay, so let's do this. So it's like 42, so I know that these two are 3, which is like a special situation for the 2 square sum. So this has to be 1, 2, right? But this already forces 4, 5 here. Like there cannot be anything else in these 2 squares, because if this is 1, this is 5. If this is a 2, this is 4. But right now, the solver doesn't do that. It's like I'm trying to think. It's like almost what I should be doing is going through the killer. Damn it, I really don't know how to implement this. Like this logic that I just described is super hard to implement. Like I can do it, like I can basically brute force it, like it's brute forcing it is not a big deal. And I can kind of special case it for like the size of 2. Like if I look at, you know, one of the squares in the killer block, does that remove possibilities from the other squares in the killer block? I could do that. And if I do it specifically for only size 2 blocks, but there's also like the situations where, like I was describing this last time, so like imagine that we have like for this 11 we know that this has to be 2 4 5, right? Well, then I cannot have a situation that this is 2 4, because if this is 2 4 5, then, you know, this would basically block it. And that kind of logic, like, these are things I do when I solve killer Sudokus, but I'm not quite sure how to implement this. Because I definitely cannot do like an completely exhaustive search, because there's way too many blocks around, like it's just too much. And then there's also like things. Okay, right now this one doesn't really have it, but like if I go to like a harder one, right? Let's say, sure, this like 10 out of 10, right? So you can have situations like, you know, basically within the single square, the killer blocks don't tell you much, but then if you take like, you know, multiple of them together, suddenly you have like 3 squares that sum up to something interesting. So this is another like big piece of logic that is missing currently, where I definitely could benefit from something like this. But that, I mean, that one is just crazy, because like you really need to consider big blocks joined together. Yeah, I mean, there's the same situation here. And from the center you kind of have the complementary thing. Yeah, there's a lot of things to think about, for sure. But I mean, at least I have the basics down, and some sort of killer Sudoku support. But like, definitely there's a place to do a lot more work here. Okay, cool. No, I'm pretty happy with the progress I made this weekend. Like, the code needs a cleanup for sure, but I think like for today that's enough. I still want to kind of work on a video anyway, so I need some time after the stream. But yeah, thanks a lot for watching, and I'm right now kind of thinking about what I will do with this project. Like I was like this, I'm not definitely stopping with the Sudoku Solver, that's like for sure. However, I'm kind of thinking about doing mixed streams, that I basically stream something different on Saturdays and Sundays. It's not really that I kind of need a break from the Sudoku, it's just that right now actually I would really like to make a progress in the UI, and right now I kind of need to wait for a new version of Clang to come out, because the current one is missing support for some of the functions I'm using in the C++20. It's kind of, I kind of made these situations for myself by just like using the absolute bleeding edge C++. But I mean, it is what it is. So I'm to a degree I'm kind of blocked by the tooling. So it kind of makes sense to just like have a break for a bit and work on something else. And I definitely wanted to have a look at like Twitch and YouTube bots, and basically have a bot that will allow me to have some interesting interactions in the chat. And especially I want to have something that when I have a short break, I want to have a bot like running quizzes and stuff, because right now it's just like dead air, there's nothing happening during the be right back screen, and there's absolutely no reason for that. Like there can be a bot running just like doing interesting stuff for people to interact with. So yeah, I might be working on something like that next weekend, waiting for the Clang to be updated. But yeah, I mean, I will be streaming something for sure. So thanks again for watching, and I will be back next week. See you then.